Right, hello Year 13s. Going to go through your mock paper. It's 5 to 3. I'm going to try and do it. I'm going to try and do it in about an hour. We'll see. It might be 2 instalments. This. So this is paper 1. It was 2025 paper. Magnesium is reacted with titanium 4 chloride. So this is group 2. Group 7 did it at the end of year 12. Magnesium is reacted with titanium 4 chloride. By the way, titanium 4 means it's titanium 4 plus, and chloride is Cl minus. So that means that you've got titanium TiCl4 is used to extract titanium metal. So we know that you're going to make that. Magnesium is reacted with it, and magnesium is Mg. So you're going to make magnesium chloride MgCl2. Just a very straightforward equation that you need to memorize and know. So you need 2 of them and 2 of them. The role of magnesium is a reducing agent. This is just knowledge. All right, you do need to know this. You can work it out. That goes from 0 to +2. The magnesium gets oxidized, therefore it's a reducing agent. This is very, very straightforward. We're dealing with group 2 chemistry here, so that was just learning from group 2. You need to know that equation. Calcium compounds for each use, so you do need to know the uses of calcium compounds. The one that we use to decrease the acidity of soil is calcium hydroxide. You just need to know it. It's in your notes. And then to remove SO2 from flue gases in power stations, you could either have had calcium oxide or CaCO3. Either of these are correct. If you remember, you can have calcium oxide plus sulfur dioxide makes CaSO3, or you can have calcium carbonate plus SO2 makes CaSO3 plus CO2. They're things, I haven't thought about them for years, but you just know them because you've learned them. By the way, a flue means a chimney. So removing sulfur dioxide from chimney gases. Magnesium hydroxide is used to relieve the symptoms of indigestion by neutralizing stomach acid. Suggest why magnesium hydroxide is safer than sodium hydroxide as a treatment for indigestion. What do you know about magnesium hydroxide? Well, magnesium hydroxide, there's the hydroxides. They get more soluble as you go down the group. There are the sulfates. They get more insoluble as you go down the group, or less soluble. What do you know about this? Well, you know that it is sparingly soluble. So you write that. Magnesium hydroxide is safer than sodium hydroxide because it is sparingly soluble. That's what you write. Don't overthink it. Just write what you know about magnesium hydroxide. It's sparingly soluble. Also accepted was insoluble. But I'd prefer to see this because that's what I taught you. All right. And the reality of this, so if you ate some sodium hydroxide, it would dissolve in your esophagus and it would start to irritate your esophagus. What you want is to eat this magnesium hydroxide. It makes its way all the way into your stomach where it reacts with the stomach acid in there. It reacts in the stomach. All right, so anyway, the answer is sparingly soluble. Next bit then. An ionic compound of a group 2 element dissolved in water to form solution X. Separate samples of solution X are tested to identify the ions. So you need to know your ions tests. So this one, the sodium's not important. They've added hydroxide and you've got a white precipitate. The only white precipitate with hydroxides that you know is MgOH2. So identify the group 2 cation in solution X was Mg2+. You had to write acid for the ion, so Mg on its own wasn't acceptable. An ionic equation, so many of you so many of you wrote half equations with electrons. It doesn't ask for that. It asks for an ionic equation, which is when you remove spectator ions. This is such a straightforward bit of chemistry. You've got to go and revise your group 2 stuff. Magnesium ions meet hydroxide ions to make MgOH2. Didn't ask for state symbols, so don't write them in because it didn't ask, although if I wanted to, that would be it. If you include sodiums in here or anything like that, you've missed the point of an ionic equation. That's the ionic equation that you needed. The other one on group 2 that you would need, it hasn't come up on this one, would be barium ions meet sulfate ions to make BaSO4. That would give a white precipitate too, but that didn't come up on this test. That one did. Right. The other test was you get a cream precipitate when you add nitric acid and silver nitrate. So when you add silver ions, you get a cream precipitate. This is AgBr, and it's a cream precipitate. Sorry, I'm making a video. Soz. I've got to go through my Year 13 mock. Okay, cheers. Right, got some people asking for help, and they can't have it. Right, identify the anion. Anion is a negative ion in solution X. That we've just identified that, it's Br minus. Give an ionic equation including state symbols for the reaction that occurs in test 2. Ionic equation, including state symbols this time. Ag plus reacts with Br minus to make the cream precipitate AgBr, which is a solid. This again was a very, very straightforward question because it gave you a cream precipitate. It's the only cream precipitate that you know. Alright, the ionic equation, whoops, I've put it in the wrong space. The ionic equation should go there. The anion was Br minus. Anion means negative ion, of course. Why is it acidified? You had to say specifically that the acid would react with carbonate ions. A lot of you just wrote would react with carbonate. You have to write carbonate ions, or you write CO3 minus. So the acid, the H plus, would react with carbonate ions because these carbonate ions would give a false positive or a white precipitate. So 1 mark for this, 1 mark for this, 1 mark for saying reacts with carbonate ions. Or, I can't remember what else you could write. I could have a look on here, 1 sec. I've got the mark scheme, just going to find it. To remove carbonate ions or to remove other ions that give a precipitate with silver nitrate. You couldn't just say other substances or other impurities. It had to be carbonate ions or other ions that give a precipitate. So not substances, they underline the ions. Give a property of barium sulfate. A property is like, you know, this idea of it being insoluble. That's a property. Something about it. It's an insoluble, or it doesn't allow X-rays to pass through it. They are properties. Some people just said barium meal. That's not a property. Okay? So, the answer is it would allow, insoluble, shows up on X-rays, radio opaque, not a word. Ignore barium meal. A barium meal is not a property. Give me a property of barium sulfate. Barium meal. Nope. Ignore X-rays if you don't say why. So it stops X-rays penetrating. So a lot of people, if you ask for a property, it's got to actually be a property of that substance. Next, this question is about ionization energies. Explain why beryllium is the element with the highest first ionization energy. And this is exam technique. Exclamation mark, exclamation mark. All of you should be looking at this. All right. Beryllium. So firstly, ionization energy is the energy when, this isn't part of the answer by the way, when you take a gaseous atom and you remove an electron from its outermost shell. You remove the outermost electron. So that's what we're going to be discussing here. So what you have is you have atoms and their outermost electron. So the difficulty in which it takes to remove this electron is to do with 3 things: distance from the nucleus, shielding, and nuclear charge. All right, as you go down a group, atoms get bigger. So the outer electrons are further from this positive nucleus. So, and as you go down the group, they become more shielded from the positive nucleus. So this is a distance and shielding. What you've got to describe is why beryllium has got the highest first ionization energy. So there's beryllium, there's magnesium, there's calcium. Okay, so what do we say? Beryllium has got the highest first ionization energy because it is the smallest atoms. It has the smallest atoms, the smallest. You have to use, what do they call them? What's those words? I've got it on here written. Superlative. Superlative. It's the smallest atoms or the smallest atomic radius or the least number of shells, the smallest number of shells. So therefore it has the strongest attraction between the nucleus and the outer electron to be lost. Okay? I saw a lot of, it has small atoms, so it has stronger attractions. Stronger than what? It has to be comparative. It has to be, in this case, superlative, strongest. All right, second ionization energy of beryllium. So we've got beryllium that's already lost an electron, Be+, gas, and we want it to remove another electron, so it'll become Be2+. How does Be+ become Be2+ gas? It loses another electron. We have an electron on this side. I saw a load of people putting it on this side. If you put an E- on this side, you'll have no charge on this side and 2+. That's not a balanced equation. Anyway, that's it. State symbols, gas, gas. Few missed state symbols there, few people did. Predict which element in period 3 has the lowest second ionization energy. Well, first ionization energy looks like this. Up, down, up, down, up. And that would be sodium, magnesium, aluminium, silicon. All right. If you remove an electron from all of these atoms, you'll have now magnesium will have the electron configuration of sodium. So basically, the second ionization enthalpy would look like this. Mg, silicon, aluminium, silicon. Everything moves down one, down the graph. So the lowest second ionization energy would be magnesium. If it asked which element in period 3 has the lowest third ionization energy, move everything down one again, aluminium, silicon, phosphorus, etc. So there you go, a little hack there for you. I didn't teach you that last year, but quite nice. Right then, figure 4 shows the plot of log ionization energy for a period 3 element. These are the ionization energy. This is removing the first electron, the second electron, the third electron, the fourth electron, the fifth electron, the sixth electron, and so on. What this tells me, you're looking for jumps, aren't you? 5 electrons were a little bit harder to remove than the previous, and then there was a big jump to the 6th. What this tells me is you are looking at an element with 5 electrons in its outer shell. 1, 2, 3, 4, 5, and then some electrons on the inner shell. So remove 1, remove 2, remove 3, remove 4, and remove 5. The 6th electron is much harder to remove than the 5th because it's in a shell that is closer to the nucleus. So I'm looking for a period 3 element with 5 electrons in its outer shell. I'll just grab a periodic table. I've only got a GCSE one to hand. Period 3 element, 1, 2, 3. 5 electrons in its outer shell, phosphorus. Alright, the element is phosphorus. Explanation, there's a big gap, or there's a large jump between 5th and 6th. Let's have a little look. Jump, large increase from the 5th to the 6th, a large jump after the 5th. The 6th electron is removed from the second energy level, or from a lower energy level, or a shell, or an energy level that is closer to the nucleus. I would say it's removed from a shell that is closer to the nucleus, because that's the easiest thing to say. Alright, 2.5, use figure 1 to determine the third ionization energy of the element. I'm not doing any calculations here. What you needed to do was, third ionization, you read this value, you read across there, which is around about 3.5. And you do, that's log 10, so you do the inverse of that log. Most people got that right because you can do that. I wouldn't be confident using my calculator to do that. Anyway, deduce the number of unpaired electrons in a copper 2+ ion. Right, periodic table. Copper. Copper's one of them weird ones, isn't it? It is argon core, 4s1, 3d 10. So copper 2+, I'm going to remove this electron and it make it 3d9, and it wants the number of unpaired electrons. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's one unpaired electron. Right, next, describe how water acts as a ligand. Describe how anything acts as a ligand, right? There's water, there's a lone pair, and it forms a coordinate bond to a metal ion. The lone pair on a water molecule forms a coordinate bond to the metal ion, or is it the copper ion specifically? Right, let's have a little look what it says. Water has a lone pair. You had to say lone pair, that it can donate to copper. Water has a lone pair that forms a coordinate dative bond to copper. You have to talk about lone pairs. Alright, you couldn't just say forms a coordinate bond. Even though that is correct, how does water do it? Got a lone pair, forms a coordinate bond to the metal. This question was well answered, so let me just talk about exam technique then, because a few of you ended up on 3 or 4 marks because you didn't really talk about it in detail. You've got 2 complexes up here, copper with 6 waters and chloride with 4. The shape of each complex ion, so I saw this, very good, octahedral, This is tetra. You didn't have to draw them. Some people wasted a bit of time doing that. Octahedral and tetrahedral was well answered. Why these shapes are different. You had to say that chloride ions, or Cl-, are bigger than H2O ligands. That had to be said. All right, so that was that bit done. Octahedral, tetrahedral, chloride ions are bigger. So this was missed by a few people. How does colour arise in complex ions was very, very well learnt. Well done, you lot. Very proud of you all. Brings a tear to my eye. Why does the CuCl4- have a yellow colour different from the blue colour? Right, okay. They've got different ligands. They've got different delta E, or energy gap. So they absorb different colours. So they have different, so they look different colours. They have different complementary colours. This wasn't explained well. Different ligands means different energy gaps, means different colours are absorbed, therefore they're different colours. That wasn't answered particularly well by a lot of you. Got a little one down here that's sort of hidden in. We probably could have done this, and some people did draw it in. I don't know why. An excess of water followed by... I can't bother. It wasn't on your test. Right. Next. Bit of a missed opportunity here by a few of you. Now, you had to put the charge on each structure. Now, it didn't tell you what the metal was, I don't think. So I gave any mark. I gave the mark for charge if you just assumed it was like a metal plus or a metal 2 plus. So let's assume this is a metal plus, and there's 2 of them. That would mean this is 2 minus. I would also have accepted 4 minus as a correct answer. Right, so what we've got then, it wants 2 stereoisomers, so I'm going to draw some square brackets. I'm going to put my 2 minus there, or my 4 minus there. I'm going to put copper in the middle. These are bidentate ligands and these are unidentate ligands. So 1, 2, 3, 4, 5, 6. We're dealing with octahedral coordination number. This bit was done well. Most people got that. Now, you've got 2 bidentate ligands. So I'm going to do that here. A lot of people went for this, oh, it's going to be optical. No, it's not. You only get optical isomers if you have 3 bidentate ligands. So it wasn't optical isomerism. You must listen more carefully in class with this. Okay, you've got 2 water ligands. So this is about cis trans. I'm going to put H2O there and H2O here. And then I'm going to correctly draw my ethane dioate ligands. A lot of people couldn't remember where to put the double bonds. If you stick to some proper chemistry and just realise that oxygens have to form 2 bonds and carbons form 4, you won't go far wrong. So that's one of them. And the other one, I'm just going to put my water molecules next to each other. H2O, C, O, C, C, O, double bond O, O, C, C, double bond O. That's absolutely fine. You have to show the coordinate bonds forming through the oxygen. I just thought it was a bit sloppy by a lot of you, really, considering we've drawn quite a lot of these diagrams in class. Yeah, and if you went for optical isomerism, you really sort of shouldn't have got it. It says ligands must be bonded via correct atoms. 1 mark for the structure, 1 mark for charges outside both of the brackets. So you had to put the charges outside both of the brackets. Next, do not write on this page. I did it on Norton. Right, next. Give the standard conditions. Right, so standard conditions are 100 kilopascals and 298 Kelvin. If you wrote this as well, 1 mole per decimeter cubed, I might have given you the mark, but I shouldn't have given you the mark. I didn't realise why at the time. If we were dealing with solutions, that would have been acceptable. But in this table, you're dealing with solids and gases, so it's not relevant, and therefore you wouldn't have got the mark. Use the equation and the data in table 4 to calculate the temperature at which this reaction becomes feasible. When you're being asked for a temperature at which a reaction becomes feasible, the equation is this: temperature equals delta H divided by delta S. And we need to just be careful and remember to divide our delta S by 1,000. So I didn't really want to see delta G equals delta H minus T delta S. I just wanted this version. So what we need to do is we need to work out delta H, we need to work out delta S, and then we're going to divide it by 1,000. So delta H then, I've got an equation up here. MgNO3 twice makes 2 MgO plus 4 NO2 plus O2. I'm going to work out delta H first for this reaction. I'm going to work this out. I've been given the formation of this, so I'm going to form that. That's minus 790. I've been given the formation of this, so I'm going to form that. There's 2 of them, so it's 2 times minus 602. I've been given the formation of this, so that's going to be 4 times 34. And I've been given the formation of oxygen, which of course is 0, because it's an element in its standard state. If I go round here then, blah, blah, blah. Long story short, delta H, when you calculate it, is 512. Delta H is 512. That's what I was looking for there for 1 mark. All of that for 1 mark. Delta S is the entropy of the products minus the entropy of the reactants. So the products entropy 27. So that's 27 times 2. 4 of these, that's going to be 240 times 4. 1 of these, that's going to be 205. So it's that lot, that's the entropy of the products, minus the entropy of the reactants, which is 164. So if you have a look, missed the 2 off there, my bad everybody, missed the 2 off. So there's the reactants. So there's the products and there's the reactants. The answer for there was 891. So delta S was 891. So I wanted to see now 512, temperature equals 512 divided by 891 over 1,000, or some evidence that 891 had been divided by 1,000, and that will give you a temperature of 575 Kelvin. So have a little look at the mark scheme. 1 mark for delta H. See, I messed that up, didn't I? I didn't put the 2 times. 1 mark for delta S. 1 mark for dividing it somewhere by 1,000, seen somewhere in there. 1 mark for T equals delta H over delta S, and 1 mark for 575. So if you just wrote delta G equals delta H minus T delta S, but didn't rearrange it like that, you're not getting the mark. Okay. Next. 4.3. Right, I can't be bothered doing this whole calculation, but I'm just going to sort of draw it out, so because a lot of people made a mistake here. NH3, 7O2, 4NO2, 6H2O. Right, the answer was 463. So for those who got that, it was easy for me to mark. I didn't have to look at your calculation. You either got 3 marks for the correct answer or 1 mark if you did something at the end, which I'll talk about. I'm just going to draw these out. NH3 looks like that. And if you've got 4 lots of them, you're going to be breaking 12 lots of 388. Okay? O2 looks like this, so you're going to be breaking 7 lots of 496. NO2, you're going to be breaking 1, 2, 3, 4, 5, 6, 7, 8. 8 lots of that. That's the bond we're trying to find out. And 6H2O, there's going to be 12 lots of this 463. So there are my sums. I'm going to go this way round and I'm going to write it out as an equation. This value is minus 1132. So me personally, I would go this value minus 1132 equals this 12 times 388 plus 7 times 496, there's my bonds broken, minus 8x minus 12 times 463, rearrange for x, divide by 8. You get this answer. Loads of you got it right. You could get 1 mark for just dividing any number by 8 at the end. That was what the 1 mark was for. We may as well look at this question now. It's a catalyst question. An alloy of platinum and rhodium, so a solid, is used as a catalyst. That's going to be a heterogeneous catalyst. Alright, so anyway. Next question, 4.5. Some ammonia and oxygen are reacted and the mixture is left to reach equilibrium at a fixed temperature. I need to just write this. out again, NH3, 4NH3, 7O2, 4NO2, 6H2O. Right, I'm just going to refer to this then, it's an equilibrium. Some ammonia and oxygen are reacted and the mixture is left to reach equilibrium at a fixed temperature. Why does increasing the temperature of this equilibrium mixture decrease the mole fraction of NO2 in the equilibrium mixture? So, I hope you all noticed actually, we didn't ask you any KP or KC. Alright, that was, missing, wasn't it? So, none of you have been asked that in this test. So, don't forget about it. KP and KC didn't come up. But this is referring to mole fractions. Right, what have we got then? Well, the value for this was minus 1120? I could just literally turn over the page and find out. Minus 1132. And that means that it's exothermic in the forward direction and endothermic in the backward direction. We're going to increase the temperature. I know this fact. When you increase the temperature, it shifts in the endothermic direction in N. Right, so how am I going to explain this? Why does increasing the temperature decrease the mole fraction of NO2? In other words, make less NO2. 1 mark for saying the forward direction is exothermic or the reverse direction is endothermic. State that first. So I would say the forward direction is exothermic. When you increase the temperature, the equilibrium will shift in the endothermic direction, and then you have to say what direction that is. To the left. To counteract the change or to oppose the change. And a lot of people didn't say that. So let's have a little look at the mark scheme. 1 mark for stating the forward reaction is exothermic or the reverse reaction is endothermic. The equilibrium will shift to oppose the increase in temperature. Sorry, you had to say it like that. Oppose the increase in temperature. I just said oppose the change, didn't I? So you have to say oppose the increase in temperature. You couldn't just say the equilibrium shifts to the left without saying to oppose the increase in temperature. All right? Oppose the increase in temperature. All right. Next. Don't write on this page. I did. Right. I've already drawn on this one. Explain why chlorine has a lower boiling point than bromine. Right, I'm looking at you, whoever it is in here, who doesn't know about why things boil. You do not break bonds when things boil, and when things boil, they do not lose or gain electrons. Get it sorted in your head. Come and see me if you don't understand why. Chlorine is Cl2, bromine is Br2. Here's a chlorine molecule. I'm going to draw some liquid chlorine, or a little diagram that represents liquid chlorine. There's a Cl2, there's a Cl2, there's a Cl2. What makes liquid chlorine a liquid is the molecules are attracted to each other by van der Waals forces, intermolecular forces. Here's bromine. There's a bromine molecule, there's another bromine molecule, and there's a van der Waals force between. All right, what we've got here, bromine has got a higher boiling point because the van der Waals forces between molecules are stronger. Because bromine forms bigger molecules or has, hang on a minute, that's why chlorine has a lower boiling point. Chlorine is smaller. Chlorine molecules are smaller. Chlorine molecules have got fewer electrons, so the van der Waals forces between molecules are weaker. Most people got this, but there are about 5 or 6 of you who are talking about electrons being lost or gained. Stop it. Think about it. Think about why things boil. Why does, when you boil a kettle, the water in there isn't losing or gaining electrons? The molecules are just separating from each other. You're breaking hydrogen bonds. Please, think. You can't go into an A-level chemistry exam not knowing why things boil. Anyway, bromine reacts with fluorine to form BrF3. Fluorine will always have an oxidation state of -1. If there are 3 of them, the bromine must be +3. Please write +3 and -1. Some people just wrote minus. Some people wrote 3 plus and 1 minus. They're technically charges, but you were allowed them, sort of. I don't like it though. It's +3 and -1. All right, I've already written on this. Some of you can't do shapes, which again is, I think, at this stage, really does need to be addressed. Draw the shapes of a BRF3 molecule. Right, bromine's in group 7. I'm going to do it in two ways. Bromine's got 7 electrons in its outer shell. 1, 2, 3, 4, 5, 6, 7. 3 fluorines are going to attach. Each are going to bring an electron with them. That means there are now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons here. If you've got 10 electrons in the bromine's outer shell, that means you've got 1, 2, 3, 4, 5 electron pairs. Right, that's my starting point. Work out how many electron pairs you've got. Another way of doing that, BRF3. Bromine is in group 7. It's got 7 electrons in its outer shell. Each fluorine brings an electron, so there's going to be 3 extra electrons there. 7 plus 3 equals 10. If you divide that by 2, you get 5 electron pairs. There's stage 1. You need to be able to do that. You don't get a mark for it. 5 electron pairs looks like this, always. 1, 2, 1 to the side, 1 forward and 1 back. Learn the shape for 5 electron pairs. It's that. I've now got to put 3 fluorines in here. I could put them, watch carefully, here, here and here. That would be fine. I could put them here, here and here. That would be fine, and actually a bit more sensible. So I'll put 3 fluorines there. That means this electron pair and this electron pair are lone pairs. That is what I wanted to see. This would also be acceptable. But I saw some just weird rubbish diagrams that showed to me that some of you didn't know how to draw the shape with 5 electron pairs, and some of you just drew shapes with 4 electron pairs, which is terrible, really. Sort it out. Come and see me. I'll help you. Look, there they go. We've got these there. The explanation of the shape. So why is the shape that you've drawn got that shape? Because the lone pairs, or the bond pairs, or electron pairs repel to be as far apart as possible. It didn't ask you to explain bond angles, it's just the shape that you've drawn. Why have you got the shape that you've drawn? In other words, why do molecules have shapes? Because electron pairs repel to be as far apart as possible. Or you could have said lone pairs or bond pairs or electron pairs are arranged to be as far apart as possible to minimize repulsion. Alright, that was it. It didn't ask you so it reduces the bond angle. It didn't ask you about bond angle, so don't say it. Solid sodium bromide reacts with concentrated sulfuric acid. Okay, I'm just drawing my diagram. If you don't understand this by now, stop being lazy and watch the videos. Alright, so this is chloride, bromide, iodide. I'm just going to fill it in. This is H2SO4 plus HX makes... hang on a minute. NaX, my bad. Plus NaX makes NaHSO4 plus HX. This makes SO2, this makes SO2, this makes S, this makes H2S. You've got Br2 there, I2, I2, I2. There's my completed diagram. Now, I know what I'm doing. If you don't know what I'm doing, you need to do some work, don't you? You've got your exams coming up. A lot of people did know what they were doing, so well done to you. All right. So, give an equation and an observation for each reaction. Which is the acid-base reaction? Well, that's the bottom one here. So that was H2SO4 plus NaX makes NaHSO4 plus HX. Actually, I've written X there, so it can't be that. Bromide, NaBr, HBr. That's what you do. I saw a lot of Na2SO4s there. Why are you learning stuff that I haven't taught you? It is correct, but learn it from what I've done. So bizarre. What's the observation? Observation is what you see. That, misty fumes. Misty fumes. That was the only acceptable answer. What's the redox reaction that occurs with bromide ions? So that was the non-redox. That's the acid base. We've now got to talk about this. This reaction here. SO2, Br2. I know how to do this, so I just can't be bothered doing it from scratch. 2H plus, 2Br minus, H2SO4, Br2, SO2, in other words, these two things, H2O. I'm not balancing it in the way I told you to balance it because it's just easier to do it like this. 2H2O, pretty sure that balances. I taught you to do it from half equations, but if you do it enough, you just know it. What's the observation for the redox reaction? You could either say choking gas or bromine. Now, bromine caught a few people out. It's an orange gas or orange or brown gas or fumes. You don't make liquid bromine, it's a gas, okay? It's a hot reaction, so you don't make liquid bromine. So I'm afraid you couldn't just give me the observation for bromine liquid. Right, iodide ions reduce copper 2 ions to form a precipitate of copper 1 iodide. Give an equation for this reaction. So I know that iodide ions, I minus, are going to reduce copper 2 plus ions to form copper 1 ions. If iodide ions are reducing the copper ions, that means the iodide ions themselves must be oxidized. Alright, so I've got my players in this are iodide, and I also know I've got copper 2 ions, copper 2 plus, and they're going to form copper 1 iodide. They're going to go to copper 1. So the iodide must form iodine because it's going to reduce the copper 2 ions. So I could try and do this by, what's it called? Doing half equations. I'll give it a go. I don't know if it's the best way with this. So the iodide's going to form iodine. So I know that iodine is going to be produced, even though it doesn't say here. And the copper 2 plus will form copper 1 plus by gaining an electron. I could then combine these two half equations by doing this. Alright, so I'll try this. I've got 2Cu2 plus reacts with 2I minus to form I2 plus 2Cu plus. Now, the problem with this is that it says specifically that you're making a precipitate of copper iodide. If you did this, I've got to say a really big well done. You've used the correct principles. But what it says you're going to form is you're actually going to form some copper iodide, copper 1 iodide. So I can't leave it like this. I'm going to form 2 CuIs, which means you need a couple more I minuses for this side. That was the correct overall equation. I think that's really hard, to be fair. I think that's the hardest bit of thinking on the paper. So well done if you got it right. What's another way of doing it? Let's see if I can work it out like this. You've got iodide ions reacting with copper 2 plus ions to make copper 1 iodide, and then you'll have to decide what else happens to the iodide. So, what's another way of doing this? I'm going to assume that the iodide forms iodine, and then I can just balance this equation. I know that hasn't been done well, but I had to think about this for a while. It took me a minute to be able to do it. Right. Hi, sir. Do you need to ask me a question? All right. That was Mr. Maiden. Do you want to say hi, sir? No, he doesn't want to say hi. Unbelievable. Right, what we've got here then is a fuel cell question. You might have noticed they've switched this diagram round to how we usually do it, but I remember that oxygen is the positive side and hydrogen is the negative side. All right, so a few people got these the wrong way round. I did tell you, though, you need to know your reactions in alkaline conditions. So the negative electrode is H2. This is the negative electrode, hydrogen. The positive electrode, oxygen reacts. So they're my reactants. Hydrogen and oxygen going in. They're the reactants. The hydrogen reacts with two OH minuses to form 2 H2O and 2 electrons. The oxygen reacts with 2 H2O and 4 electrons to form 4 OH minus. Oops, we've got a prayer going on. So what I'll do, I'll just pause it. Okay, so prayer's finished now. So they were just 2 easy marks if you knew them, 1 mark if you got them the wrong way around. But if you did it in acid conditions or you didn't know them, well, of course you're not getting those easy marks. Why is it not necessary to replace the KOH electrolyte during the operation of the fuel cell? A lot of guesses here, because it was fairly tricky. But if you notice, at one electrode, OH minus is being used up, and at the other electrode, at the positive electrode, so at the negative electrode, OH minus is being used up, at the positive electrode, it's being produced. That is why you don't have to replace the KOH electrolyte. Right, describe how the reactions at the electrodes generate an electric current. Again, let's look at these. At the negative electrode, electrons are produced here. They are then going to move through the external circuit, through the motor, and they are going to be used at the positive electrode. So I wanted this idea that electrons go from the negative to the positive, 1 mark, and they go through the motor or through an external circuit for the 2nd mark. Okay. The fuel cell uses pure oxygen rather than air as an oxidizing agent. Suggests the identity of a gas that would react with KOH. The only thing in air that's reactive enough to react with hydroxides is CO2. The other gases you've got is nitrogen, completely inert. Oxygen, you can't oxidize that. Nothing will happen. It's carbon dioxide. I don't know if you know that from organic, actually. When an alkaline hydrogen-oxygen fuel cell is used to power the motor in a car, the hydrogen can be stored as a liquid. I love this idea that people are going, liquid hydrogen is less explosive. Not at all. No. If you want to store hydrogen gas as a liquid, you've got to compress it. All right? And when you compress a gas, it takes up less space. That was it. Takes up less space. Takes up less volume. Occupies less volume. Okay? Anything to do with cost or safety or transport? No. I don't really want to carry around a tank of compressed hydrogen gas, because if I crash, it will all explode and then I'll be in a mess. Alright, anyway, fuel cells, that one. That's just learning that. Fuel cells, as long as you keep providing external fuel, they'll give you a voltage forever. An acidic hydrogen-oxygen fuel cell has different reactions at the electrodes, but why is it the same as that as a hydrogen? Why is the EMF the same? Same overall reaction. Most people got that right, so well done. Alright, what block of the periodic table? The blocks of the periodic table are called the S block, the D block, and the P block. There is no such thing as the 3D block, there is just a D block, so you just have to write D or D block. Why can vanadium be pulled into thin wires? So this is a GCSE question about why are metals ductile, or why are they malleable? So layers of, in this case, vanadium or metal atoms can slide over each other. Alright, that was it. If you've got, there's vanadium, alright, and they arrange like that, sabpidel, they're not overlapping, they're not meant to be overlapping. These layers of metal ions can slide over each other. Not easily, you have to pull them, but they do slide into wires. Right, this question then. Tin reduces VO2 plus in acidic solution. So here we go, there's tin, and there is VO2 plus, this one. Use the data in table 6 to deduce an overall equation for the reaction that occurs. Okay. This is more positive than this. So what's going to happen is the tin is going to turn into tin 2 plus, and the VO2 plus will turn into VO2 plus. However, you've now got VO2 plus. So a secondary reaction will happen. The VO2 plus will turn into V3 plus. So you had to write an overall reaction for this, and it was very, very poorly answered because very few people spotted it. If you wrote V3 plus as a product, though, you did get a mark. I think I maybe saw 2 fully correct answers. So how would I go about this? Well, I think the simplest way, and this is important, because how do I combine these 2 half equations, these 3 half equations, to give me an overall? Well, what I can do is I can think about what we start with and what we end with. I know that the tin is going to end up as tin 2 plus. I think this is a fairly sensible way to do it. I know that the tin will turn into tin 2 plus, it'll go that way. And I know that the VO2 plus will end up as, not this, but this, V3 plus. I think this would be my preferred approach. So what I'm going to do now is I'm going to balance these half equations. 2e minus there. How does VO2 plus become V3 plus? Well, the vanadium's balanced, so I'm going to put 2 waters on this side, 2 H2O's there. I've got 4H plus. 4H plus there. Now this side is 3 plus, this side is 4 plus, this side is 5 plus, so I'm going to put 2 electrons there. This would be my preferred approach. So I would now write Sn plus 4H plus VO2 plus makes V3 plus SN2 plus 2H2O. I ain't arguing with you. That was a tricky question to get right. 1, notice that it's V plus would get you, V3 plus, that'll get you 1 mark, and then balancing an equation overall would get you another. Alright? Another way of doing it, I suppose, is to go, right, when tin turns into 2 plus, that's 2 electrons, and for VO2 plus to go to V3 plus, so that's 2 electrons. So that and that are going to cancel out, because that gets made and then used up. So you've got tin reacts with VO2 plus and 4 hydrogens to make V3 plus and 2 H2Os. But I think that's quite an advanced way of doing it. Right, why does vanadium sulfate has a high melting point? Yay, GCSE, vanadium sulfate, ionic, metal, non-metal. Many strong electrostatic attractions between oppositely charged ions in a lattice. Yay, it still works. Compound Q is found in crude oil and has this molecular formula. A sample of Q is ionized by electrospray ionization. Electrospray ionization is when the sample, Q, is given an H plus from the volatile solvent and becomes QH+. That's all you had to write. Did it want any state symbols? Nope. 1 mark. You could also have written it like this. C33, H34, N4VO4 plus H plus makes C33, H34, N4VO4 H plus, like that, or you could have written H35 in here, whatever, but that was the easiest one. That's the easiest question on the paper, by the way. Alright, this thing here weighs, now I'm not going to work it out, I'm just going to look into the mark scheme. Where are you? Can't find it. Oh yeah. This thing weighs 601. This thing, sorry, weighs 602. 602. It wants, didn't want that, sorry. What's the M over Z? That just means what's the mass? The charge is 1, right? So what's the M over Z? It's asking you what the mass is. It's asking you how much this weighs, and the answer was 602. You just spend a bit of time adding all that up. Look back over your mass spectrometry notes, please. Right. Now then, a sample of vanadium contains vanadium-49 and vanadium-51. The relative atomic mass of vanadium in this sample is 50.97. So I know that 50.97 equals the mass of this times its abundance. So I want to work out its abundance, right? 51 times x. So I'm going to do 51x. Plus the mass of this one, 49, times its abundance. Now, its abundance is going to be 100 minus x. So if this was like, if this one's abundance was 9%, this one would be 100 minus 9 would be 91%, okay? Divided by 100. This statement got you 1 mark. If you solve that for x, you get 98.5%. That was generally well done, but a few of you are a bit out of practice with that. Then we're on to acid bases. So what I'm going to do there, it's school is finished. I'm going to stop today because I don't know how to answer acid bases questions particularly well. I'm going to do a couple more questions. Right, this answer was done really well. That was just fine. It's a strong acid. You do, what is it? You've been given the pH. It fully dissociates in water, so it's minus log 10 of 0.15. 0.82 is the answer. I would have write that pH equals minus log 10. God, it's been so long since I've done this. Something like that, and then you inverse log it or whatever. Propanoic acid is a weak acid. The answer was 0.123. This was generally well done. You had to work out the concentration of H plus first, which was, I'm just going off the mark scheme here, 10 times minus pH. You know what? I'll show you the mark scheme. So, Mark 1 was for writing down the H plus concentration, which is 10 to the minus 2.89. So that's what I was looking out for, this number. Ka, you then had to write there, which is H plus squared over HA, or written like this. And then the third answer was rearranging that to work out the concentration, which is 0.123. So just did that. I could do the next page though. Right, so this is when we're adding something. So this is, to me, you started off with something that is acidic down here. Now that's weak acid to me. That's like pH 4-ish, and that's a weak acid. Wow. And it's finishing off at pH 12, so that's a strong alkali. Weak acid into a strong alkali. This is the start, and this is the end. So it's weak acid, strong alkali. Yeah, that one. I mean, I haven't done that. It's just like I just looked. That's where you start, and then you add this, and it ends up here, pH 12. And I know pH 12 is strong alkali. Anyway, different indicators change colour across different pH ranges. There were 3 to tick here. This one, and this one. How do you do that then? You're going to get an indicator that's going to work in that sort of range. Is that right? So anything in that range would work. Them 3. Right, a lot of people didn't tick enough boxes. Right, gonna stop. Because I can't face doing it anymore. I've done about an hour now. So that's 51 minutes. Part 2's coming at some point. Or it might be part 2 in class. Enjoy! Bye.